Hello, everyone. Thank you for joining the Modeling Complex and Unique Systems track of the virtual ASFPM conference. We have three very interesting presentations for you today that I think you're all going to really enjoy today. My name is Zach Witten. I work for Stantec. I'm going to be moderating today's session. I hope everyone's enjoying the conference so far. It's a very unique experience being able to enjoy these presentations from the comfort of our living rooms, offices, and the comfort of our PJs. So I hope everyone's enjoying this unique experience of working or this virtual experience from home. But hopefully soon we'll be back together and enjoying this conference as a whole again soon. You've probably heard how this is going to go from multiple people or from the other sessions, but for anyone who's just now joining us, I'm going to kind of go over how the presentations are going to go and how we can get the Q&As done. And I will apologize in advance because I'll probably repeat myself between the other presentations. So in a moment, we are going to start with the first recorded presentation. And during that presentation, if you have any questions about the presentation that you would ask the presenter, you'll put it into the Q&A box on the side of your screen to ask that question. And at the end of the presentation, I will be on there to read it to the presenter afterward. There won't be an actual Q&A session where you get to physically ask the question to the presenter. I will be asking those questions to the presenter from your typed in chat box. And hopefully we'll get through all the questions in 30 minutes, but if not, we'll have to cut it short. In the event that we get through all the questions and we still have some time left before the next presentation, I am going to wait until that next 30 minutes to start the next one, the next 30-minute time slot, just in case someone's coming from a different presentation room into this one. I want to make sure that they hear the full presentation. So with that, I'm going to get started with our first presentation. The first presentation is by a Dr. Stefanovic. Apologize if I said that name wrong. And the presentation is evaluating downstream impacts of flood control projects by Streambed Mobilization Energy. So Dr. Stefanovic is a senior technical project manager with HDR, and he's been with them he has had 25 years of experience working on water resources on a wide range of clients, particularly the Army Corps of Engineers. His primary area of technical expertise involves the integration of surface water hydrology, multidimensional hydraulics, sediment transportation modeling, and river mechanics. He has received the prestigious Strobe Award from the St. Anthony Falls Hydraulic Laboratory for his doctoral thesis in hydraulic engineering and was honored by the American Academy of Water Resources Engineers. And with that, we are going to start the presentation.
Hello, everybody. Welcome to my presentation. This is the first time we meet virtually, and I hope to see you all in person at the next conference. Today, I will talk about evaluating erosion impacts by streambed mobilization energy downstream of flood control features, specifically related to the Truckee River Flood Management Project. This is a highly visible project that HDR has been performing for the Truckee River Flood Management Authority in Nevada. The Corps of Engineers, Sacramento District, and the cities of Reno and Sparks and Washoe County are working together on this project. The Corps is the federal sponsor, while the three communities have formed the Truckee River Flood Management Authority, known as TRFMA. Let's meet the river first. As the only outlet for Lake Tahoe, the charming Truckee River offers a range of recreational activities, including fishing, river rafting, kayaking, and sightseeing. However, about every 10 years or so, the Truckee River overflows its banks, causing tremendous damage to residents, businesses, and infrastructure. For example, in the 1997 New Year's Day flood, damages exceeded $1 billion over 6 counties, and the frequency of damaging floods appears to be increasing with climate change and extreme weather events. So the primary goal of the Truckee River Flood Protection Plan is to reduce flood damages and casualties from a 100-year flood event. Also, providing passages for fish spawning, enhanced recreational opportunities, and restoring more than 50 miles of the Truckee River between the city of Reno and Pyramid Lake have also become important supporting goals. The flood control project is being designed and built in cooperation with the Corps of Engineers. Other federal funding partners include the Fish and Wildlife Service, Bureau of Land Management, Bureau of Reclamation, and FEMA. In the summer of 2014, the Flood Protection Plan received formal authorization from the Congress, and this major milestone was accomplished after over 15 years of Corps of Engineers exploration and planning. Typical project elements include building levees and flood walls, acquiring and protecting flood-prone lands, relocating businesses and elevating homes, replacing bridges, excavating floodplain terraces, restoring ecosystem functions, and enhancing recreational areas. This is the Reno-Sparks metropolitan area. Combined, it has a population of nearly 500,000 residents and is known informally as Truckee Meadows. The project is now focusing on the flood risk management and is confined to a smaller footprint completely within Truckee Meadows. The Vista Narrows Reach, with approximately 8.5 miles of flood control improvements, introduces increased flows to the downstream reaches of the river due to levee confinements. The agency TURFMA recently initiated a fluvial geomorphic study for a 54-mile river reach to assess downstream impacts of flood control improvements on the river sediment transport capacity and erosion potential. This study serves as a screening effort to understand the potential geomorphic impacts on the downstream reaches with respect to changes in inundation extents, changes in flow velocity and riverbed shear stresses, potential for sedimentation impacts, bank erosion, and lateral channel migration, particularly at 7 critical areas of concern where significant bank cuts and meander migration was observed. As part of this study, a comprehensive bed sediment sampling program for the 54-mile study reach has been developed and led by HDR. We developed a sediment sampling protocol to identify best locations for collecting surface and subsurface sediment samples. It's important to understand that sufficient sampling of the stream bed should be conducted to determine the spatial variability, size, and gradation of the bed material. The general rule is to carefully select sampling locations and avoid anomalies that would bias either the calculated sediment discharge or the calculated bed stability. And typically, mid-channel and diagonal bars are preferred sampling sites exposed to highest velocities, which typically transport largest materials. Point bars are not as ideal because velocities are highly variable there, and sidebars are the least desirable locations in zones of low velocity due to boundary effects. The sampling sites were selected away from zones of active bank erosion, as the material deposited in the channel near the eroding areas may not be representative of the sediment reaches. Although bridges provide good access, bridge crossings are also not appropriate sampling sites because they are typically located at natural river constrictions, or their abutments and piers create constrictions and local scour. Dead water areas behind sandbars or other obstructions were also avoided, as they are not representative of average flow conditions. And this map shows 4 typical sampling locations in red circles along the 54-mile reach of the Truckee River. This is our crew of the Geotechnical Subconsultant CME. They were conducting underwater pebble count at 54 locations in November 2019, which was quite a heroic effort in a 50-degree Fahrenheit cold water. At each location, they collected the surface and subsurface samples. Overall, 108 samples, which took about 5 weeks due to unfavorable hydrologic conditions in the river. The final product of the sampling are these gradation curves at each location from a geotechnical sieve analysis. Here you can see the difference in bed material size with depth. For example, at this location 1, the surface material has a median particle size D50 of 25 millimeters, while the subsurface material is only 3 millimeters. And many locations along the river are armored this way by coarser material, and we accounted for that in our streambed erosion potential analysis. At 5 critical locations with severe bank cuts and meander migration, bank samples were collected for direct shear tests to identify geotechnical stability parameters, soil cohesion, and internal friction angle. And these parameters were used in our fluvial geotechnical stability analysis and lateral bank retreat evaluation based on a model of wedge-type bank failure caused by Tosgauer. The overall concept of the flood control project on Truckee River relies on compensating for loss of flood storage in Truckee Meadows by increasing discharge into the downstream Truckee River Canyon. This increase in discharge is accomplished by widening and constriction at Vista Narrows and constructing about 4,000 feet of a new levee with 2 miles of terracing. And this design lowers floodwater surface elevations in the area by enhancing the constriction points, which keeps water from backing up and allows more flow to be conveyed downstream during large storm events. Based on HDR's unsteady flow simulation for proposed conditions, the 100-year post-project discharge is increased about 11% at the peak, while flows are increased over a period that is about 15% of the total hydrograph duration. However, the Truckee River 5-year hydrograph, which is shown on this slide, is minimally impacted by the proposed project, and these flows are mostly responsible for long-term geomorphic work that forms the channel. It is also important to realize that based on the Truckee River flow duration curve, which is shown here, geomorphically significant flows less than 5,000 CFS, which are not impacted by the project, occur more than 99% of time in the 30-year hydrologic record. Now, when we talk about fluvial geomorphic evaluation, there are several techniques to evaluate potential fluvial impacts in streams. And I'm trying to use the color coding here to signify the level of complexity and cost with each method. For example, you can use a hydraulic model to determine average channel velocity, bed shear stress, and corresponding stream power for any cross-section and any flow. These are straightforward and depend on availability of HEC-RAS model. More involved are the incipient motion analysis, where you compare the shear stress to critical shear stress of bed particles, and also scour analysis with relevant scour components. Even more complex is a bank retreat analysis and sediment transport capacity, which require specialized tools for evaluation. And on top of the complexity list and cost would be a full-blown mobile bed sediment transport modeling using, for example, HEC-RAS or HC6T. Now, a special category is this streambed mobilization energy approach listed at the bottom of this list, which is still simple and robust, somewhere between green and blue effort on this complexity list. So what is the stream bed mobilization energy? The potential for stream bed erosion and mobilization of surface bed material driven by fluvial processes needs to consider both the magnitude and of hydraulic stresses applied on the stream bed during a flood event, as well as the duration of the flood event. So to incorporate the effects of both magnitude and duration, the potential for fluvial processes to contribute to stream bed erosion along the Truckee River study reach was quantified using the total stream bed mobilization energy exerted by a single flood event. This energy, E, is defined as the integrated product of the excess stream power above the velocity threshold for the bed particle movement, expanded on the stream bed and the incremental time over which it is applied. Of course, I don't expect you to remember all this, but just pretend for the moment that you enjoy integrals as much as I do. The key here is that the stream power, which is the product of velocity and shear stress, is integrated over the entire duration of the flood event hydrograph to directly evaluate the effective geomorphic work responsible for the channel formation. This critical channel velocity we see here is the same one you use to determine either live bed or clear water scour conditions, for example, when you calculate bridge scour, and it depends on the medium particle size, D50, and hydraulic depth for each discharge. Evaluation of the stream bed mobilization energy is based on the HEC-RAS model results, velocity, shear, and hydraulic depth. We use the Truckee River hydraulic model that was initially developed by the Corps of Engineers for a 54-mile reach from Vista Narrows all the way to Pyramid Lake. So the procedure is essentially to discretize the flow hydrograph into a series of histogram blocks with certain duration, and each block is set up as one steady flow profile in HEC-RAS. The hydraulic model provides average flow velocity in each cross-section with a corresponding shear stress and hydraulic depth, and the rest of the procedure is really a spreadsheet exercise where the critical erosion velocity is calculated for the collected bed sample, D50, and hydraulic depth. The incremental stream power is then determined for each flow and multiplied by its duration to come up with an incremental energy. And ultimately, summation of incremental energies for all the flows is equivalent to integrating over the entire hydrograph duration, which provides the total stream bed energy in each river station. Now I'm showing our final results. We looked at several erosion critical downstream reaches and averaged the results over multiple cross-sections representative for each location. And I'm showing the results for the 100-year hydrograph on the top and the 5-year hydrograph on the bottom for both pre-project and post-project conditions. In a relative sense, two reaches carry the highest stream bed energy, South Hollywood and Numana Dam in this table, which means that they exhibit the highest potential for surface bed scour. On the opposite end are Big Bend here and Paulina. As you can see, even though the maximum local increase in stream power is about 18% for post-project conditions in this James Ranch Road reach, the maximum erosion energy has increased only 4% in that reach for the 100-year flood. In fact, there are two reaches, this Big Bend and South Hollywood, where the energy dropped for post-project conditions, indicating less erosive impact for the project conditions. Another important conclusion from this evaluation is that the project has insignificant impacts on 5-year flow, doing 99% of long-term geomorphic work. In summary, The streambed mobilization energy technique was developed in this work to evaluate potential for erosion of surface bed material and downstream project impacts from increased flow or other project design features affecting fluvial erosion. Very important is to remember that this tool incorporates both the magnitude of hydraulic stresses and duration of the flood event, which is essential for proper evaluation of project impacts. It is a physically sound methodology that directly evaluates fluvial energy responsible for geomorphic work that forms the channel, and our recent application to 54 miles of the Truckee River confirms that the method is simple to use. It's basically post-processing HECRES results from multiple profiles. It is robust and its predictions are consistent with erosion trends that were observed in the field. However, this methodology is not intended to provide definitive conclusions regarding the actual stream bed degradation during erosive flood events or to supply design parameters for any remediation measures. It is a screening level tool for evaluating relative impacts in erosion critical reaches that may require further geomorphic slope stability or sediment transport analysis. This concludes my presentation. Thank you for your attention, and I hope to see you all in person for the ASFPM 2021. If you have any questions in the meantime, or just want to say hi, my email is listed here. Stay safe, wash your hands, and now you can start touching your faces while I'm closing this presentation. Goodbye, everybody.
Thank you, Draghi. That was a very interesting presentation. We do have one question so far. Currently, it looks like Draghi is having some issues with his microphone, so maybe he'll be able to get on and answer us here in a moment. But Draghi, if you can hear us, the question that we have so far is, would the concept of streambed energy integral be applied to the downstream power of a stormwater, of a stormwater system? Stormwater flood channel, sorry. Were you able to get that, Draghi? Unfortunately, it does seem like Draghi is having some issues with his microphone. So hopefully if he can get that back on within the next 8 minutes, he'll be able to answer that question. Thank you for your question, Phil. Hopefully we can get to that. In the meantime, I guess we do have about 8 more minutes until the next presentation, and we are going to wait that full 8 minutes before we get going. So if you want to kind of take a break, get some, refresh your drink, your food, whatever you need, go ahead and go do so, and then we'll be back in 8 minutes.
Sorry, I'm having issues with the sound.
microphone fix for Draghi. And so for Phil, I'm going to repeat your question for Draghi to hear. So Draghi, the question is, could the concept of streambed energy integral be applied to the downstream power of a stormwater flood channel?
Yeah, I mean, there is no problem to apply that integral to any fluvial reach. The important thing is that you have a hydrograph discretized, form those discretized blocks of constant flow. Then you evaluate your, stream power and stream energy for each cross section, and then you average them over a number of cross sections.
Excellent. Thank you, Draghi. That was the only question that we had so far. So I am still monitoring the Q&A box, the chat box. So if another question does kind of come up, we have a few more minutes for you to ask those questions. So feel free to type them in there if you have another question, or Phil, you have a follow-up to Draghi's response. So we'll kind of wait here a moment for that. And Draghi, thank you for the presentation. I enjoyed that. That was very interesting. So, and I don't think you're the only one who enjoys integrals. So.
Yeah, thank you.
All right. Does not look like we're having any more questions popping up. So I guess we'll just give it a few more minutes for the next presentation to get queued up, and we'll get started with the next presentation. So thank you everyone for their patience.
Thank you.
We did have another question pop up. Two questions have popped up, Draghi. Hopefully we can get this in real fast. So the first one is any value to talking about the difference between frequent and infrequent events?
Well, that's the beauty and power of this tool, because it can address both the magnitude and duration of the event. So that's exactly what is important in evaluating downstream impacts, downstream geomorphic impacts, the duration and the magnitude. So this tool is able to evaluate both effects, and one of them is the duration, which is very important.
Excellent. Thank you very much. And looking at the time, unfortunately, that is the last question that we're going to have for today. Hopefully, if you have another question, you can find a way to reach out to Draghi, but we are pressed for time. We do need to move on to the next one. Again, for anyone who's just joining us, just a quick recap. So if you have a question that pops up during this next presentation, please use the Q&A chat box on the side of your screen to ask the questions. We'll be monitoring that, and we'll ask the Q&A afterward. Our next presentation is Lacustrine hydraulic modeling of Lake Champlain, and it's got two presenters. We have Rebecca Starosta and Christopher Ott. Christopher and Rebecca are water resources engineers with AECOM and part of the Compass PTS JV. They have been with AECOM for 6 and 8 years respectively, and their experience has consisted primarily of hydrologic and hydraulic modeling for FEMA flood studies. including the FY17 study of the Clinton County, Lake Champlain, which they're present on today. Chris received his bachelor's from UMass Amherst and his master's of environmental and water resources engineering at Virginia Tech. Rebecca received her bachelor's and master's degree in civil engineering from the University of Maryland. And with that, we are going to get started with the second presentation.
And welcome. Thank you for selecting our presentation today among the many that are going on. Today we will be presenting on the hydrologic modeling of Lake Champlain, which was part of our recent FY17 Region 2 study. With that, my name is Christopher Ott. I am a civil engineer with AECOM. I've been there just about 6 years, and with me today presenting is Becca Starosta. Becca?
Hi, I'm Rebecca Starosta. I'm a project manager and water resources engineer with AECOM, also based in the Germantown, Maryland office. I've been with AECOM for almost 8 years, working mostly on riverine H&H for FEMA risk map studies, spanning from discovery to post-preliminary processing nationwide, but mostly working in regions 2, 3, 4, and 6.
Thanks, Becca. For today's agenda, we will be covering Lake Champlain, the historic flooding that the lake has experienced throughout the years, our FY17 Region 2 study that covered Lake Champlain and Clinton County and adjacent New York County, and the hydrologic modeling that went into the study. And then finally, we'll wrap up with looking forward into the future, some goals and expectations we have. With attendees from around the nation and possibly the globe, we'd like to start by setting the scene and familiarizing you with Lake Champlain, such as where it's located, the general hydrologic features of the lake, and some general characteristics of the project area itself. So where is Lake Champlain located? If you're having some trouble on the map, let me help you out. So Lake Champlain is located mainly within the United States in New York and Vermont, forming a portion of the border between these two states. A portion of the lake is also located in the Canadian province of Quebec. So some important things to note about the lake is that it flows from south to north, shown by the arrow. The lake water is discharged to the north via the Richelieu River, and it is in the Lake Champlain Valley between the Adirondack Mountains of New York and the Green Mountains of Vermont, shown on the right side of the slide. And much of the lake's coastline is relatively undeveloped, but there are several cities located along the lake, including Plattsburgh in New York and Burlington, Vermont. So let's jump right into some hydrologic characteristics of Lake Champlain. Some things of note is that it's a natural freshwater lake formed by glaciers with an immense drainage area of over 8,000 square miles, has almost 600 miles of shoreline. The greatest width of the lake is right around 12 miles between the city of Port Kent, New York and Burlington, Vermont. The average depth of the lake is around 64 feet. And something I should note is that the lake depths vary quite a bit throughout the lake. The deepest part of the lake has been measured about 400 feet in depth. Also, the lake temperatures vary quite a bit from season to season. Around June, July, and August, the recorded temperatures of the lake can average out around 70 degrees Fahrenheit. And in summer or in winter months, the lake drops in temperature quite a bit. And there have been accounts of the lake surface completely freezing over for the complete lake. Also, most of the inlets of this lake are high gradient streams that peak within 24 hours in response to precipitation or snowmelt. In most of the mountain basin, a high percentage of the winter precipitation is stored in snowpack. This makes spring snowmelt the dominant hydrologic event of the year, with nearly 1/2 of the annual stream flow typically occurring in a 6 to 8 week period in the spring. So the project area itself is located like in New York and Vermont, as stated before. The climate of the region is categorized as humid continental, with long cold winters of sub-zero temperatures and short summers. The project area is residential, but attracts a lot of tourists, primarily for recreational activities, and the area has great drinking water. One other big draw of Lake Champlain is, of course, Champ. And if you don't know who Champ is, I will tell you right now. Lake Champlain's well-known monster, Champ, was first identified back in the 1600s by Samuel de Champlain. And it's actually, he's actually very popular up in this region. So now Becca is going to be talking a little bit about the historic flooding that Lake Champlain has experienced. Becca?
So based on the hydrologic and geographic characteristics that Chris mentioned, you can probably guess that most of the flooding for Lake Champlain occurs in the early springtime. The conditions most conducive for flooding along the lake are in the winter, where you have the freezing temperatures and lots of snowfall, followed by a warm and rainy period in the spring. And this combination has occurred in varying intensities in the past and has resulted in flood damages and flood along the lake. The average annual water level of Lake Champlain is 95.5 feet. This varies seasonally, of course, but anything above 100 feet is considered flood stage for the lake. This table shows some of the highest historic flood water levels for Lake Champlain. As expected, most of them fall in that March to May time period, so you have that spring snow melt and also the rains. So the flood of record is the May 2011 flood, so a recent event where the lake reached a flood stage of 103.2. As you can see, that's considerably higher than previous events. The return period for the May 2011 flood exceeded the 500 year. As mentioned, it was the highest lake levels and flows ever recorded for the lake. Is attributed to record snowfall in the area, followed by an intense spring rain. This figure here shows the ice coverage from April 8th to May 1st. So as you can see, there was a lot of ice in April and it melted, and that's all going into your basin, contributing to that flood stage level. And Lake Champlain stayed at flood stage for 67 days from April to June 2011. These are some of the pictures from the 2011 floods. Just to give you an idea of kind of magnitude. The cost of flooding was estimated to be $90 million in damages across Canada and the US, and this was for homes, businesses, roads, bridges, and other infrastructure. And that was with damages in New York for over 900 homes, in Vermont for over 200 homes, and in Quebec damages to over 2,500 homes.
Thanks, Becca. With the record flooding in 2011, FEMA recognized the need to update the flood study for Lake Champlain and its surrounding areas. As a result, the Lake Champlain Clinton County study was scoped in FY 2017, and preliminary products for the project were issued in late February of this year. So a little bit of background about the effective products for Clinton County. Prior to the new preliminary products, the previous effective study for the project area of Clinton County, New York was a countywide study that went effective in 2007. However, it was more of a compilation of community-based FISs and didn't include updated engineering analysis. The engineering analysis behind the effective firms were completed in 1970s and 80s, meaning it was pretty old modeling, and a lot has changed in these past 40 to 50 years, such as land use, development in these project areas, new topographic data, more historical records from gauges, and newer models software to update our engineering analysis. Something else to note is the effective study for Lake Champlain used graphical frequency analysis with one gauge station. I believe it was at Rouse's Point, New York, with records from 1869 to 1976. You can see in this figure where Clinton County is in New York, the top right corner of the state, or northeast. And what was looked at for the study was we remodeled and mapped over 720 miles of Zone A approximate riverine mileage, and updated over 70 miles of detailed streamline. The resulting preliminary products consisted of updated flood insurance rate maps, updated flood insurance study reports, and firm databases. So also the primary portion of the study was Lake Champlain itself, and something to note is Lake Champlain serves as the entire eastern border of Clinton County. This figure gives you a sense of how big the lake is compared to the county itself. The yellow shading in the figure shows the Lake Champlain Huck 8 watershed, and the thick green line shows the extent of the restudied New York shoreline of Lake Champlain. Now, the Vermont shoreline was a part of the study and was restudied, but since New York is FEMA Region 2 and Vermont is Region 1, this study's preliminary products only include the New York portion of Lake Champlain. So Becca's going to be talking a little bit about what went into the hydrologic modeling of Lake Champlain.
Thanks, Chris. So now we're going to discuss the hydrologic modeling for Lake Champlain that was performed for FEMA Region 2 as part of the FY17 study. So after careful evaluation of potential methodologies and available data, the project team, along with FEMA Region 2, determined that gauge elevation analysis would be used for Lake Champlain modeling. And this is a summary of the steps that we'll cover in the next few slides. So the project team first did data identification and collection. Generally, one of the first pieces of data checked for in hydrology and hoped for is the availability of gauge data. For Lake Champlain, there's 5 USGS gauges available in Lake Champlain. As you can see in the figure here, they're fairly uniformly distributed along the lake, about 30 miles apart, with 3 gauges on the New York side and 2 gauges on the Vermont side. The period of record for the gauges varies from 5 to 150 years, and all the gauges have daily elevation or stage data available. So having several gauges with a good period of record helped to determine what methodology would be used for the lake. Obviously, having gauges available with a long period of record is important when you're proceeding with gauge elevation analysis. Another thing to note is that gauges measure the lake elevations regardless of the source of inflow. So whether it's snow melt or rain on snow or flood runoff, it also accounts for the seasonal variations, which is important in this project area. So also part of the initial data identification and collection, the project team performed a literature review and looked at existing studies for Lake Champlain. One of the things that they noted from previous studies is that in the late 1960s, previous studies noted that there was a permanent rise in lake levels of about half a foot. This was attributed to physical changes to the outlet of the lake, including adding fill for residential settlement and also the widening of the Champlain Canal into the river, which caused a constriction for the outflows of the lake. Additionally, the Richelieu River in Canada has a very flat gradient. It's about a 1 foot drop over approximately 21 miles of length. So previous studies noted that this flat gradient coupled with vegetation and sediment deposits also attributed to the half a foot increase in lake levels in the late 1960s. So to support the water level shift noted in previous studies, the project team used several methods to determine, 1, if the gauge data supported this, and 2, to determine the cutoff period for the gauge frequency analysis. Some of the methods used to identify the cutoff period included double mass curve analysis, split sampling, and moving mean analysis. So the latter two reveal that there is a sharp shift in the observed data statistics between the late 1960s and the early 1970s, as shown in the figure here. And so with the split sampling and moving mean analysis coupled with the literature review, as well as project communications that we have with USGS and NOAA representatives, It was determined that the shift in statistics and the shift in lake levels occurred in 1969. So this box and whisker plot summarizes the lake elevation statistics before and after that cutoff period of 1969. In this figure, the red point there shows the sample mean of the daily elevation data. The top and bottom horizontal lines are the first and third quartile of the daily elevation data. This is for the Burlington gauge. And the second quartile, the median data, is shown by the middle horizontal line inside the box plot. So as you can see, there's definitely a change in statistics before and after that 1969 cutoff period.
Thank you, Becca. Along with data identification and data consistency checks, data independence and extension was paramount for this 2017 study. Autocorrelation analysis was utilized to test the temporal dependency of the observed elevation data. Along with that, a data extension method described in USGS Bulletin 17B, also known as the two-station method, was used to extend data at stations with shorter period of record to develop equivalent lengths of record between gauges. The Burlington station was chosen as a base for this method and was applied to the three other stations, Whitehall, New York, Port Henry, and Grand Isle, Vermont. For our gauge elevation analysis, the Army Corps' HEC SSP package was used. HEC SSP stands for Hydrologic Engineering Center's statistical software package. It's a mouthful. But basically, gauge data was loaded into the package, which performed a frequency analysis, ultimately providing statistical or static surface elevations or stillwater elevations for Lake Champlain. This also incorporated the use of the log Pearson type 3 analytical frequency analysis and the Weibull plotting position method, also the inverse square distance interpolation, which calculated the spatial average frequency elevation values for Lake Champlain. So our resulting stillwater elevations can be seen in the table figure above. The 1% being 102.38 feet. I should note that. And below is a comparison with the results from the 2007 effective stillwater elevations. And you can see that there is a 0.68 feet elevation increase between studies. And now I should reiterate that the effective study for Lake Champlain used a graphical frequency analysis with one gauge station versus our use of 4. And the age of records was a lot older. And for mapping purposes, for the effective study, the 1% and 0.2% floodplains, also known as the 100-year and 500-year, were mapped based on a 1966 topographic data of contours of 10 and 20 feet. So here we have the resulting 100-year floodplain of Lake Champlain. The 500-year is not depicted here, but will show up in the preliminary products of the 2017 FY17 study. So now looking forward. We did issue preliminary products in late February of 2020. The Community Coordination Officer meeting went off without a hitch in late April, and we look forward to the June open house, hoping there will be no delays. And then ultimately with the effective issuance of the study. Following the completion of our 2017 Clinton County Lake Champlain study, we have some important goals to keep in mind. We would love to continue to influence decisions when it comes to development, ordinances, and flood mitigation projects in the area, help maintain the sustainability of communities by increasing resiliency to flooding, and communicate with citizens the risk of flooding. Now, that being said, I'd like to bring up the Richelieu or Lake Champlain River International Flood Study. The 2013 international study looks into the future flood controls and mitigation for Lake Champlain. The 2015 technical group focuses on flooding risks, possible solutions, and forecasting and mapping tools. And we included a link at the bottom of the slide if you'd like to dive in. So with that, I would like to thank everyone for their time and hanging in there with us for this presentation. And I would like to now open the floor for questions. Thank you very much.
All right, thank you both for that presentation. I really enjoyed that. So far, we do have 2 questions. I'll start with the first one from Dan. He writes, great presentation, we agree. To what extent are you coordinating your efforts and vice versa with the International Joint Commission Lake Champlain Richelieu River Study?
Sure. Hi. Thanks for the question. And so the study work was mainly performed as part of FY17. So we finished the study in 2018. At that time, the IJC study was still underway. So we had a few coordination calls with them where mostly they were interested in learning more about our study and how it could be utilized for theirs. And unfortunately, at the stage their study was, there wasn't much of being able to take data from their study. Just kind of a little background on the IJC for Lake Champlain. Well, the IJC, of course, kind of oversees international bodies of water, such as the Great Lakes and Lake Champlain. They've also kind of been in charge of determining for Lake Champlain, kind of like studies in the future of the lake. And so one of the things in the 1970s is they looked at possibly regulating the lake levels. It was determined to not proceed with that because of the potential environmental impacts. And so following that, they recommended doing the flood forecasting, more robust flood forecasting system, which is what the IJC study for the lake was currently.
Thank you. The second question was Bulletin 17B or updated 17C?
I can take that one. Thanks for that question. That's an easy answer. Bulletin 17C wasn't available at the time, so Bulletin 17B was used instead.
Excellent. So we had a third question come in. Effect on existing homes within higher flood elevation. How was this communicated to the owners?
Sure. So, okay. So currently the study, part of the FEMA study, there's the risk map process that kind of goes through different stages. So currently we just completed the virtually held CCO meeting, which is with the community officials. And following that, we're going to have an open house with the study area. And that's also probably going to be done via telephone, given the current conditions. And before that as well, following the finalization of the modeling and mapping, we had the flood risk review meeting, which is with also the community officials. And at that time, many of them will share it with their constituents and also citizens. So following kind of the open house, that's when the general public is on the phone, in this case, able to ask questions and see the new results and presentation.
Excellent. Thank you. And that is the last question that we have. If you have another one, I'll wait about a minute. There's a pretty long delay between the questions that we receive and then how we can address them. So hopefully I see a question pop up soon. But if not, I just want to say thank you again to Rebecca and Chris. I enjoyed that presentation very much. So thank you for that. And yeah, we'll give it another minute for any more questions to pop up, and then we'll move on to our last presentation of the track. Nothing seems to be coming through here. So at that, I will stop this presentation, again saying one last thank you to Rebecca and Chris, and we will move on to the next and last presentation. This next presentation is the innovative combined coastal inland flooding models and solutions for use of coastal / estuarine areas to enhance resilience. This presentation will be given by Johnny Martin. Mr. Martin provides coastal and hydraulic engineering for projects at Moffatt and Nichol, ranging from beach nourishment, shoreline protection, stormwater management, flood mitigation, and large watershed studies. He's been with the firm for 26 years and is currently serves as the water practice lead for the company. And with that, I'm going to turn it over to the presentation, again, for our last presentation of the day. So thank you, and enjoy the presentation.
Meeting with you guys today and talking about a project that I've been involved with a long time, or a number of projects, and we've seen a couple of them be put in the ground over the last 10 years or so, and have some exciting results to share. But just the title of my talk is Innovative Stormwater Solution in Coastal Areas. This has been some work that's been ongoing for probably the last 10 to 15 years, and anyway, just excited to share it with you today. So again, a lot of it has to do with some work that we've been doing along the barrier islands here in North Carolina, but it's applicable in other spots as well. Of course, what's unique about barrier island hydrology is you have the ocean on one side, the sound on the other, and then you have this sort of system of dunes and troughs along the way, and then of course the flat areas around the sound. And of course, since there's not usually a lot of natural drainage features, what you end up having is flooding that occurs in these trough areas that ultimately still end up getting developed as well. So here's just some pictures showing some, these are along the Outer Banks of North Carolina around Nags Head. You can see some of the flooding in some of these low-lying areas. This is along the beach road. Here's some modeling results from some monitoring data that we had, monitoring wells that we had been put in place, and collected data for about 2 to 3 years. And you can see some of the maximum water depths during some events can get up to 1 to 2 feet deep in some of these deeper troughs. Of course, it makes for some interesting recreational opportunities, as you can see here, but in all seriousness, especially here in North Carolina, along the barrier islands, they kind of use the waste system as a way to control development. So on most of our barrier islands, you have septic systems. You do not have centralized sewer. So the issue is, or one of the big contaminants of concern, is fecal coliform. So what happens is, of course, as these water levels rise, you have septic field inundation, you have fecal coliform counts that can easily get into the hundreds to the thousands and tens of thousands. Of course, rainfall is, statistics are increasing in many places. We're seeing it along our coastlines with the additional or the increased frequency of extratropical and tropical events. And so we're seeing that happen, and just as a resiliency measure, you're seeing that these areas are experiencing flooding a lot more than they even used to even 10, 20 years ago. So what we found in these systems is that the site characteristics, of course, are really important to describe those, and that's what drives the behavior as well as the response of the systems. So again, with the topography, we normally are looking at a dune trough system. Land use vegetation, whereas historically before development there was probably a lot of natural vegetation, a lot of vegetative uptake. That of course is been greatly reduced with development. Of course, one of the things that you do have working for you are normally the sands are relatively clean. You do have on occasion some organic pockets and a shallow confining layer. The groundwater levels, they're usually high in the low-lying areas, especially in the troughs. Tides, they can impede groundwater transmission. Of course, as we've already said, the rainfall and water quality concerns that also are important to describe. So when we're doing these systems and studies, a lot of times what we are looking at, there's doing some geotechnical data collection, looking at measuring the hydraulic conductivities, both for the saturated zone and the unsaturated zone. And in a couple of these, especially some of the initial ones we've done, we've spent a lot of time doing water quality testing and wetland surveys to determine, are we changing the hydro periods of both the areas that we're pumping from as well as where we're pumping to. Here's just an example of the water quality sampling data. This is from Emerald Isle. So what I will say here is what we started doing was doing some testing in an area of the island and looking at the P's denote sort of groundwater wells, and at the same location these S are surface samples. So what you can see, there seem to be some issues with the first set of some contamination issues of the person who was doing the test. But if you look at these next three, what you can see is at the same location at the same time, groundwater sample would have fecal coliform counts less than 1, whereas surface water counts could be in the hundreds to thousands and getting close to 10,000. The measurements here are for wells located at the natural area that we ultimately helped the town get a grant to purchase, that we ultimately are pumping water to. So some of the new modeling tools that we've used, this is just showing you a graphic of the Mike Shee model that we've been using for these barrier island studies and looking at coastal resilience from sort of the rainfall perspective. Again, what's unique about it is it really solves all phases of the hydrologic cycle, both interception and evapotranspiration, overland channel flow, as well as groundwater flows for unsaturated zone and saturated zone flow. What we do is you can put in grid inputs. This is the topography. This is the horizontal hydraulic conductivity. You can put in vegetation maps with different leaf area indexes. You can get as complex as you want to, different soil mappings for both the 1D equations used for the unsaturated zone, as well as the 3D equations used for the saturated zone. This is the initial potential head that we put in for, this is for the Kerala study. What you can see here is you see the freshwater lens that is sort of having the peak in the middle of the island. But one thing that was really interesting, and we've seen this in all the areas that we've studied, is there also seems to be a gradient along the island that also we've seen has a bit of an impact, and especially when you're putting in groundwater management systems, what you can find is as you put them in different phases, you can help other areas in the interim while you're waiting for funding to put systems in at a specific location. So these are just some of the modeling results that we had for, again, this is up at Kerala. This was flooding during an 8-inch rainfall event that we then used to help calibrate the model. This was flooding during a 16-inch rainfall event. I believe this was during Isabel. And you can see the areas of water depth greater than 2 feet in these trough areas. So we've looked at different treatment options and then have installed a couple. We were involved with a pilot study where we were looking at some inline systems of treating surface water for biological contamination or fecal coliform and enterococcus. What we found with those systems is that with this level of with these fecal levels and enterococcus levels, that even if you get 50% treatment, you're going to have a very difficult time reaching standards by the time you get to end of pipe. Because again, for swimming and some of the recreational uses, you're looking at enterococcus levels down to 14, fecal counts, down in the 50s. So anyway, it's pretty difficult to reach that with inline systems. What we have found, though, is with groundwater collection and pumping, we have found that, again, using the in situ sands as a sort of treatment mechanism, as a sand filter, and then being able to proactively pump down these groundwater levels when they see an event coming, it can provide an additional capacity and limit the septic field inundation and keep the water out of those areas. And again, what really drove this home was the fact that historically what these communities would do is that they were allowed to pump water over to the beach once the water level got 14 inches over the roadway for emergency vehicle access. So there again, when the water levels got up to the point, at that point they had inundated the septic fields, the fecal coliform counts were through the roof, and then you were allowed to pump it to the beach. So we thought that this would be a way to sort of be more proactive and to keep the water levels from ever getting up to that point, except in really extreme cases. So in Emerald Isle and Currituck County, the monitoring data for these systems is promising. The pumped groundwater fecal levels are much lower than ponded surface samples. The agencies over time, they've allowed pumping to upland areas, and now we are able to actually pump it to surface ponds as long as there's not a direct connection to the sound. Receiving areas are needed. Of course, these systems are fairly expensive because you have force main and pump infrastructure that's needed. And then in the case of Currituck County, where they wanted to put in generators and SCADA controls, that also added a good bit of cost. So here's just some of the monitoring data to take a look at. These were actually samples done right at the discharge point of the pipe. So what I'll do is I'll go ahead and show you the Emerald Isle system. So what we had was these pumps through here that were then coming to this 40-acre tract. And then, so this was the first system that we ever got permitted. So the agencies wanted us to have a nice natural area for this water to go into and infiltrate in before it goes out to the sound. But so the first measurements I'm going to show you are right at the discharge point before it is polished or enters into the wetlands at all. So you can see here that over the 2.5 years of data that we went out and collected, you can see that the fecal coliform counts at the pump, right at the pump discharge, were less than 1 or 2, except for this one time, and we did see scat at the location at this time. But you can see every other occasion the fecal coliform counts were less than 1, and that's the water that's even entering into for the other treatment. These monitoring wells are located within that area I showed you along the property. You can see 3, all less than 1, all less than 1. Like this well, we felt like that it was damaged. There's also in this area a lot of deer. I mean, this is the last 50-acre tract that was not developed within Emerald Isle. So as you can imagine, there's lots of wildlife. But the water quality sampling wells at 9, which are right before it enters the sound, always less than 1. So we were really pleased to see these results. I'm just showing you this to get an idea of the system. This is Currituck County up in Kerala, where NC12 ends on the northern Outer Banks. What you can see here is the phasing of the system. So we put in these different systems along these east-west, or I'm sorry, these east-west streets, and that could pump to either this pond or to this pond here. And so the phase 1 was toward the south. And what I was meaning before is that we saw that there was a gradient of groundwater from sort of, well, this area is north, so along this axis. And what we found was people in Dolphin were saying that their flooding levels were less once this pump system at Marlin was put in, because it was intercepting some of the groundwater transmission that was coming from north to south. Again, this is the Emerald Isle system that actually pumps to an area, a passive park that is now full of, that it has treatment wetlands. This is what these systems look like being installed. You can install them along the right-of-ways. This is what Emerald Isle has been doing. What Currituck County has been doing, they had some east-west streets that they were looking to replace and get rid of for maintenance considerations. So they actually took these streets out and put in dry detention basins with accesses, and which did require driveway relocations, as you can imagine, and a lot of interaction with the property owners. But anyway, at the end of the day, it helped sort of kill 2 birds with 1 stone. This is just sort of a graphic or a picture showing the generator system that they put in at Currituck County. To the right, I'm showing here sort of our infiltration system, 24-inch perforated HDPE pipe with a sock around it with a rock matrix. It's about 8 to 10 feet down, depending on where we're at. And you can, of course, what I'm showing here at the bottom is just sort of the slight influence. So we're not putting these way down deep. So this is not New Orleans or anything else where we're having massive drops in the groundwater table. And we also are very careful as far as the permitting to talk about how often these can be operated and the floats being set. Speaking of which, just here's a computer grab of showing the system at Currituck County. What's interesting to see here is sort of the drawdown and recovery. So you can see the graphic here of the water levels measured within the pump station, drawing down, recovering, drawing down, recovering. So as you can imagine, there's lots of calculations that go into the optimal pump sizing from both a cost perspective and the amount of pipe needed to feed into the wet well versus how many of these you're going to put in versus the receiving capacity of where you are pumping to. Of course, since we are mainly looking at pumping groundwater, the response time does take a little while. So what I tell people is that, you know, you can proactively manage just before the event, but depending on the size of the event, you may have surface flooding, but the duration will be much less than what you've seen in the past. And that's what we have seen. Excuse me. So these are just a couple of graphics of talking about what the client's perspective is. And what we found in both of these areas is that essentially what we can handle in both areas has been about 6 inches of rainfall in a 24-hour period. So if we see much more water depth than that, it's going to overcome sort of the natural infiltration capacity as well as what these pumps can do. But we're really pleased to see that they could be really effective even to events up to that. So that's, you know, between a 10 to 25 year rainfall event, even with the new statistics along eastern North Carolina. This is just some other experience notes from people who worked on the Currituck project. One who was a drainage board member who also worked with the Corps of Engineers. I was just really pleased with the municipal agency, the firm, and the public work. Again, we would go twice a year and just update them as different phases were going in and talking about how much the system had pumped and, you know, how much flooding probably had been avoided. And again, really pleased with the performance during nor'easters and small hurricanes and these events that we are seeing much more often. Again, during a Florence where it's dumping 30 inches, you know, over a couple of days, we're not going to be able to handle that. But I will say that those were the areas of town that were able to recover quickest. So as far as resiliency goes, being able to be proactive as well as recovery, these systems are meeting that need. As far as costs go, the Emerald Isle system has been roughly, from the town's perspective and the infrastructure, roughly $2.3 million. Again, they are keeping their systems within the right-of-way. This doesn't include the purchased property of the property and the park, because that was sort of dealt with on separate funds. But as far as being able to put the system in, that's what this cost was. As far as Currituck, theirs was more expensive just given all the driveway relocations, the streets being taken up, as well as the generators and the SCADA system that were put in place. $8.3 million, and that was paid for by a special task district set up for the Wellhead subdivision. So with that, I'll be glad to, again, just pleased to present this information to you today, and I hope that it has been helpful and educational. Thank you.
All right, thank you very much, Johnny. That was a great presentation to kind of close us out of this session. Really enjoyed that. So far, we have one question that's come up on this. Again, if you have any questions, please get them in quickly. There is a delay before it gets to us. And so unless I want to make sure I don't miss the question, but the question we have so far is, so 8 inches and 16-inch rainfall depths are infrequent, ? And that's a question for me too, seeing as how 8 inches in the state of Arizona is PMP level. So.
Right, yeah, great question. So, yeah, so in North Carolina, especially with the new Atlas 14, we have seen, so of course, some increases, and of course, with just the tropical events we've had. So, you know, roughly, we are seeing these 8-inch rainfalls over 24 hours in now about once every 10 years, 10 to 25 year events. So the 16, yes, is still really extreme, but as we kind of said during the presentation, we're really happy to see that these systems could actually work fairly well and keep flooding down up to even 6 inches over a 24-hour period, which is somewhere now with the new statistics within between a 5 to 10 year event. So it was even better than what we were expecting. But yes, it's we have seen a significant jump in sort of our rainfall depths, just again basically due to hurricanes, as well as, and not you give me this soapbox, I will say, as an older guy, you know, one of the things I've been trying to think about people getting answering this question is when we look at the old statistics, you know, that were put out by technical paper 40 and 62. I had an old hydrology professor at State that made us go back and look at that, and you see that most of the statistics were based on maybe about 15 years of data, because most of the gauges went online in 48. So, you know, one of the things I always have wanted done is for National Weather Service or someone to say, how much of these increases are due to a length of period versus really this increased storminess? So I'm still waiting for that answer, because I think that would really help us in this resiliency work that we're trying to do and trying to look at these different levels of uncertainty.
That's a great point. I'm glad you kind of added that in there. I didn't realize that there was only 15 years of records for that TP40. 2 more questions have popped up. First one, are E. coli levels monitored in the park area where the water is being pumped to? Do residents near the park have concerns?
Right. So on one of the slides, we did show the 9 wells that were sort of within that 40-acre tract that we were pumping to. And as you could see that even in that area, the fecal counts were less than 1. So, you know, that really allayed the concerns of the nearby residents. There were a couple of times when we did see some elevated levels, but again, that 40-acre tract is pretty much now where a lot of the wildlife lives. So there's a lot of deer. So there's just a lot of natural scat that also happens there as well. But everything that we measured for a period of about 3 to 4 years, and we found that the water going out into the sound are being discharged even times when we had that outlet open were cleaner than the water that was actually in the sound itself. So that was encouraging.
Excellent. So the last question deals with, he was going to ask about financing, but he answered it. But apparently there's a Netflix show called Outer Banks, and he's curious if you've watched it. I don't know if there's some correlation to the flooding in the Outer Banks show. So that's a pop culture reference I'm not sure about. But the question is about Outer Banks with the TV show. I don't know if that has something to do with this area, as far as if there's flooding involved with that.
Right. So yeah, I haven't caught that one yet, but my understanding, you know, just being a native North Carolinian, is actually there's been a lot of stuff said that it was actually filmed in South Carolina. So there's some people that are kind of upset that it wasn't actually filmed up in the Outer Banks, that it was filmed in South Carolina. So any of the flooding you see there is South Carolina. So.
All right, I'll keep, if I ever watch that show, I'll think about that. So it's funny. That's the last question that I have. Again, I think with that, we'll kind of conclude the session. I think that, again, thank you for the time. Johnny, it was a really impressive presentation. I really enjoyed that. Thank you for the Q&A. I appreciate everyone who came to this track of the modeling complex and unique systems. It was a very good 3 presentations. So thank you all for joining. I hope you enjoy the rest of the conference, and have a great rest of your conference. So goodbye, everyone.
Thanks, Zach, for a great moderation. Thanks.
Appreciate that.
All right.